In this video, we discuss eliminating 0 over 0 indeterminate forms by 3 methods. First, we factor and reduce. That's one we've done before. We factor and reduce whenever we were evaluating limits of rational functions. We're going to show a couple of simple examples here. And we're also going to show examples where we multiply by the Pythagorean conjugate their complex fraction. In each example, we will do the calculations, and then we'll look at the geometric interpretation. We'll draw a graph ourselves, and then we'll confirm that our graph is what it's supposed to be by looking at the corresponding graph on Desmos.com. So let's look at this problem first. We have the limit as x approaches -3 of 2x plus 1 times x plus 3 divided by x plus 3. Typically, this problem will be given to you where this is distributed, and you'd have to factor it yourself. But if you didn't have to factor it yourself, if it was written like this, you could just say, okay, is this function continuous at -3? Well, if you want to know, you just plug in -3. 2 times -3 is -6. -6 plus 1 is -5. And then we've got -3 plus 3, which is 0. We have -5 times 0 divided by 0. And that means we've got a 0 over 0 indeterminate form. If you notice that you have a 0 over 0 indeterminate form, you factor, and then you cancel common factors. So you'll probably have to factor by grouping or factor by guessing, but you'll factor. And then after you factor, we see that we've got an x plus 3 in common in the numerator and denominator. So we say as long as x is not equal to 3, that's a number divided by itself, which is 1. So you can reduce that. You might be saying, but aren't we interested in x equals -3? I'd say we are interested in x equals -3, but we're not actually ever going to get there. We want to get infinitely close, arbitrarily close to -3. So we can cancel those. The limit of this function is equal to the limit of this function. So we cancel those, and then we say, is this function continue at -3? And it is. It's just a line, a linear function. So we can substitute in -3 for x. We get -3 times 2 plus 1 is -5. And that tells us that as x approaches -3, the y values in the graph approach -5. So x equals -3, y equals -5 is an open circle on the graph. And the graph is going to look like this. Y is equal to this function, which is the same as that linear function, as long as x is not equal to 3. So you're just going to graph the line. Just make sure that you put an open circle on the graph at x equals -3, y equals -5. Now this one is similar. If I substitute in x equals 1 here, 1 squared minus 1 is 0. And of course, 1 minus 1 is 0. So this is a 0 over 0 indeterminate form. And as soon as you notice that it's a 0 over 0 indeterminate form, you can say, okay, if I'm dealing with a rational function, I'll just factor. This is a squared minus b squared. A squared minus b squared factors to a plus b times a minus b. In this case, a is x and b is 1. We've got an x plus 1 times x minus 1 divided by x minus 1. Now we're saying as x approaches 1, we want to look at this function. If we plug in 1, again, we get 0 over 0. But the x minus 1s are in the numerator and denominator. So we can reduce those and look at the limit of the resulting function. Limit of this function is the same as this function, and this function is continuous at 1, so you plug in 1 and you get 2. And that means as x gets infinitely close to 1, arbitrarily close, as close as we want to 1, the y values get arbitrarily close to 2. So x equals 1, y equals 2 is a hole in the graph, and the graph looks like this. This function looks like the graph of y equals x plus 1, which is just a line with a slope of 1 that passes through x equals 0, y equals 1. And at x equals 1, y equals 2, we have an open circle. That's the only point that's missing on the graph of that line. Okay, so now we've got another example. I've actually already worked this one out. I did the explanation already, and I accidentally failed to record. I forgot to record, so now I'm recording it again, and I've already done the calculations. But let's say that this blue part wasn't here. Let's say you were just given this problem. It's got a square root in it. And you say, okay, what's the limit as x approaches 4 of this function? Well, if I can plug in x equals 4 and I get out a number that makes sense, then that's our answer. That's exactly where we want to go. So try substituting in x equals 4. Well, 13 minus 4 is 9. Square root of 9 is, the square root of 9 is 3. So you have 3 minus 3, which is 0. over 4 minus 4, which is 0. So that is a 0 over 0 indeterminate form. So you say, okay, how can I get rid of that 0 over 0 indeterminate form if I can't factor it? I mean, I can't factor it because of the square root. You say, well, I can't factor, but maybe if I multiply by just the right thing, I'll be able to factor. And I notice that I've got this 3 minus the square root expression. And that reminds me of these Pythagorean conjugates. The conjugate of a plus b is a minus b. The conjugate of a minus b is a plus b. They're going to have the same form, except you're adding them instead of or you're adding rather than subtracting, or subtracting rather than adding. You just change the sign in the middle. If you multiply those together, you've got a times a is a squared. A times, or first times first is a squared. Outer times outer is negative ab. Inner times inner is positive ab. So those reduce, and then last times last is negative b squared. So you'll always get a squared minus b squared, this difference of perfect squares if you multiply by the conjugate. So we're going to multiply by the conjugate. But you want to be careful here. The whole goal is to get rid of that square root. So you don't want to change anything under the square root. Leave what's in the square root alone. You're going to change the sign in front of the square root. So you have a 3 minus the square root. The conjugate's going to be 3 plus the square root. Now, if you're going to multiply by 3 plus the square root, that's okay. That's legal. As long as whatever you do in the numerator, you have to do it in the denominator, so you don't change the value of the function. So we do the same thing in the numerator and denominator. And then in the numerator, we're distributing. And the whole point of distributing is to hopefully get a polynomial expression that we'll be able to reduce with something in the denominator. So you distribute. First times first is 9. Outer times outer is 3 of those square roots. Inner times inner is negative 3 of those. So you add those together and you have 0 of them. The square roots are gone. And then last times last is that negative times the positive, which is negative, times the expression inside or under the radical. And don't forget your parentheses there. You want to subtract the entire quantity, 13 minus x. So we've distributed in the numerator, but you want to leave that denominator alone. The reason we're leaving the denominator alone is that we're hoping that after we simplify this numerator, we'll be able to cancel with that x minus 4, that factor that was equal to 0 up here. So we distribute the negative. We have a negative 13, and negative times the negative x is a positive x. Got that. And then 9 minus 13 is negative 4. Negative 4 plus x is the same as x minus 4. So you can write that in different order. You get this. And you got x minus 4 divided by x minus 4. And those are the same as long as x is not equal to 4. So since x is not equal to 4, you can cancel those. It's going to give us a 1 left in the numerator. And then the denominator is just this expression that's left. And so you say, okay, after factoring and reducing, simplifying and then factoring and reducing, we've got this 1 over this function. Our question is that function continuous at x equals 4? And it is. If I plug in 4, 13 minus 4 is 9. I have the square root of 9 which is 3. I have 1 over 3 plus 3, which is 6. Or 1 over 3 plus 3 is 6, but then you're taking 1 divided by 6, and 1 6 is your answer. So you can plug in x equals 4. So just do it. Plug in x equals 4, you get this. Simplify, you get that. You no longer need the limit notation here because the limit of this function is this number. And now we know that as x approaches 4, the y values approach 1, 6 on that graph. So we know that that's what it looks like. I don't know exactly what this original function looks like, but I know that as x approaches 4, the y values approach 1, 6. Let's see what it looks like on Desmos.com. So this is the graph of the first function. It's a line with a hole in it at x equals -3, y equals -5. The limiting value is exactly what we'd expect. And then we just did this example where we multiplied by the conjugate and we found a limit of 4, or we said that when x approached 4, the y values approached 1, 6. So we're here. And just to see if the limit is what it's supposed to be, I draw that open circle, and if I zoom in, I can see that the limit is what it's supposed to be. It says x approaches 4, y equals that 1, 6, and it looks right. I think we must have done our calculations correctly. That's it. It's kind of a weird function. It's well defined from -infinity to 13 apparently. has this kind of weird range from negative infinity to whatever that y value is. Right there, when x equals 13. Is 3 divided by 9, 1/3. But yeah, that's the limit that we were supposed to calculate, and it looks like it's the right limit. So we finished this Pythagorean conjugate example. We did the factor and reduce example, and the last one is to clear complex fraction. I'm going to do that in another video. I have to go right now, but we'll do that in the next video. But we've got both of those here. So we'll do the clearing complex fraction in a future video. Thanks so much.